Yeah, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So let's um, discuss the chapters on multiprocessors, multi-core, and real-time scheduling. So our focus on this chapter will be multiprocessor and multi-cores, and then real-time scheduling in the form of real-time OS. Okay, so this is the outline of these chapters. So we'll discuss the granularity, how big for synchronizations. Okay, because if you have one task, then it's the granularity, whether it's big or you have a smaller one to synchronize. Okay, you can divide it into smaller tasks. Okay, then what are the design issues on multiprocessor and multi-core schedulings? And we have two things here. We have the process scheduling and we have thread scheduling. If we know from the previous chapter, one process, then you can have the part of executions. You can create fork a new thread, and then this one will be join, close the thread. Okay. Then let's see how we do the multi-core thread scheduling. Okay, the next one we have real-time scheduling, the characteristics of real-time OS, deadline scheduling, rate monitoring scheduling, and the priority inversion. Other than that, then we have here the Linux scheduling, Unix scheduling. This is SVR4, and this is the FreeBSD scheduling that is on the Mac OS. Okay, then we have the Windows scheduling. Okay, so the learning objective for these chapters is to understand the concept of thread granularity. Okay, how big is the task that you want to synchronize or you want to divide? Okay, and discuss the key design issue in multiprocessor thread scheduling and some of the key approach to scheduling. Okay, so now is the era of multi-cores because you can what you call them. We have previously we have only one processor, okay, uniprocessors. Then around 2000 and above, we have now multi-core, okay, or multi-core. Previously, also we have SMP, symmetric multiprocessor. So two uniprocessor combined into, you have the two socket in the motherboard, okay, and you have here the symmetric multiprocessor. But now we have in one package, we can have the multi-cores, okay. Okay, then real-time scheduling, RTOS, and then see the example on Linux, Unix, and the Windows. Okay, so let's discuss first the multiprocessors and multi-core scheduling. Okay, as you see here, this is multi-core. We have core number 1, number two, number 3, and number 4. Okay, so let's see the background first. When a computer system contains more than a single processor, okay, several new issues are introduced into the design of the scheduling function. So previously, if you have only one processor, then if you remember the queue, the 5-state process models. Okay, so we have start, okay, ready, run, and this is if you are doing I/O, you have block. Okay, so if you're doing I/O, go to here, and then go to ready, then process finish. Okay, this is process finish. Okay, so this is if you have only one processor. Okay, what happens if you have two processors? Then you can see the run part. For example, you have two processors and you have two run part. This is the design issue, whether you want to have one ready queue, okay, one ready queue, or you have each one has its own. Okay, one go to here, one go to here, and go what you call go back here for idle. Okay, when you select another process or another thread. Okay, so this is a design issue. Now, if it is 2, now you imagine if you have 16, if you have 64, now Threadripper also has 128 cores, then you need to manage differently the core and the thread. Okay. Okay, so multiprocessor system can be classified as follow. You have loosely coupled or distributed multiprocessor or cluster. So you have the collection of PC like this. Okay, and you have also functional specialized processor. This is like the I/O processors. You can have what you call, you have also like in NVIDIA, you have the core here. This is the von Neumann architecture. you have the memory, and you have the I/O. One of the I/O is the VGA, graphic card, GPU, and in GPU it has its own video memory as well. Okay, so this is functionally specialized processor. Or you have something called the video processors. You have the sound processor or signal processing DSP, the digital signal processor for sound, for video, or the security. Okay, to manage the encryption in your computer. So this is the functionally specialized processor. Okay, the other thing is you have tightly coupled multiprocessor. Of course, different thing. Now you can see you need to have different framework, okay, to maximize the processors. Okay, one is distributed, one has different memory. You can see here. Although now we have a uniform memory, okay, you can use from video memory or vice versa. The GPU, if not enough, then you can use also the computer memory. Okay. Tightly coupled microprocessor is like for human architecture. You have two cores and you can have the shared memory. Okay. Okay. So this is the picture. This is the server motherboard. As you can see, you have CPU number one, CPU number two. Okay, so and you have here so many memory bank. Okay, one, two, three, four. You have four memory bank. Okay, as you can see here, this is normally in the form of SMP, symmetric multiprocessor. So you have core socket number one, socket number two. Not necessarily also one processor. You can have also 16 processor. Okay, 16 plus 16, then you have 32. If you have AMD Threadripper, for example, 64 plus 64, 128, and so on. Okay. So this is SMP. You can so in the form of the core. Okay, you can divide into the core, or you can put like in the cluster. As you can see here, you have uh, this one. This one is normally using the shared memory. Okay, because they can access the set memory. Okay, not sure about the motherboard. Maybe they have uniform access or they have non-uniform access. Means that this one is preference for this CPU socket, and this two you have connected directly to this one. So if you want to connect to this from CPU number one to CPU number two, then you need to go through CPU number two to get access to the memory. Okay. Okay, but here the cluster. So this is Raspberry Pi cluster head, and this is the cluster computers. You can see the Beowulf cluster. You can connect standalone PC and connected to the. You can see here this is the connection, the Ethernet switch. Okay, so now this is become distributed memory. This is shared memory, okay, in which the memory is shared among cores. You can see here, this is the memory shared, mean that it can be accessed by CPU number one or CPU number two, or you can see it's in the form of distributed memory. So each one has its own memory, PC number one, PC number two, okay, and then connected to the communication line, okay, like Ethernet, Wi-Fi, and so on. Okay, so you can see the different. This is the distributed memory. Okay. Okay, so this one also has system bus. You can see this one has system bus. Not necessarily one processor, can be also two processor. You can see this is connected using the system bus. You can have the I/O is on also. Okay, but different PC, then you need to connect using the communication line like Ethernet and other things. Maybe fiber optics also you can use to connect between PC. But you can see here system bus will be very fast. There's some issue there, then this one will be slow. Okay, so you can connect multiple computer like this, but it has the trade-off. Okay, if you remember the alpha, the uh, MDES law, the speed up is one of alpha plus one minus alpha divided by number of processor. Okay, or number of PC. Okay, so you can see here alpha is part of the alpha or serial portion is the communications. Okay, communication, synchronization, critical sections, and initialization. Okay, that's the I/O, also the I/O for that contributing to the alpha. If alpha is high, you can see speed up will be lower. Okay, here alpha is very small. Okay, so that the speed up will be higher. Okay, here alpha, because of this, the communication line, it will be higher, so the speed up will be slower. But in a way, it will be faster also compared to if you use only one computer. Okay, so let's move on. Now we see the concept of granularity. You have the work. Granularity is how big is your work to be distributed. You can see this is coarse, very coarse, medium, and then fine. Okay, you can see then this one becomes smaller. Okay, this is the grain size. Okay, you have the task, then you can distribute. Okay, so parallelism inherent in single instruction stream. Okay, this is synchronous interval is less than 20. So this is, for example, in a multi-core system. Okay, multi-cores in which you can have parallel instructions. Okay, medium, parallel processing or multitasking within a single application. So means that you are using the thread from one process, then you can create a various thread. After finish, then you can join. Okay, so this is the medium. Quartz, multiprocessor of concurrent process in multi-programming environments. Okay, so you can have multi-cores, and then you can have that you can overlap. Okay, you can do overlapping. Okay, very fast distributed processing. What is processing? The one that we have here earlier. This is the very fast one. Okay, because the reason why it's very fast, because you don't want to distribute it. You want to minimize the communications. Okay, remember that this is slow. This part is slow. Okay, you want to minimize the communication. So that's why normally you divide by two and distribute. Okay, so that's the reason. Okay, so very fast. This is the internal instruction. Or independent, you have the multiple unrelated process. There's no synchronization. For example, you have open Microsoft Word, you have open Chrome on your other monitors and so on. That will be multiple unrelated process. Okay. Okay. Okay, now let's see the independent parallelism, the first one first. So it's not connected. There's no explicit synchronization. So each operating separate independent application or job. Okay, like I mentioned, one open PowerPoint, and then you type also in Microsoft Word. You search using Chrome and so on. That the independent. Okay, there's no explicit synchronization. Okay. This common in time sharing system, so word processing or using spreadsheets. Okay, the benefit you need when you utilize multiprocessor, we improve the average response time. So this is if you have two process, for example. Okay, if you have one processor, you can do interleave, but when you do have two process, then you can run at the same time. So this is overlapping. You can see you only can do interleave. Here you can do overlap as well. Okay, so at the end, when you measure this one will be shorter, mean will be faster. Okay. Okay, so we can compare the distributed system requires networking for set resources. Remember we have here, this is the networking. Okay, so this is distributed system. Okay, or you can have also shared multiprocessor system. You share the memory. Okay. Okay, so let's move on. Quartz and very quartz grain parallelism. Remember, the very quartz is and the distributed, and the quartz is the multiprocess. Okay, multiprocessing. Okay, so the synchronization among process. So normally we are on the process level. This is suitable for concurrent processes. Okay, you open multiple process at once. Okay. So this is easily supported by multi-program uniprocessor. You have process A, process B. If you have one processor, you can do this. All multiprocessors, okay, you can overlap. Okay, you can overlap. So this is multi-programming. You have multi-program running at the same time. Okay. This one has minimal interaction between process. Okay, because of the very cost. Okay, just need to interact. For example, when you start, you check here start process B, for example, it will check indirectly how many more memory is available on the system. Okay, then it will check. You can allocate. Then if A is here, then B is required this much. Then you can allocate B here. Okay. So the use case, for example, the example here, parallel compilation, you can spawn process to compile files simultaneously, achieving speed up. Okay, so this is in this distributed computings, and also when you do the parallel compilation. So you have, for example, source 1.c, your source 1, source 2.c. You compile this one into the object. Then you combine later on. Okay, after the compilation. When you do multiple compilation, then it has speed up. So you need to open compiler 1, compiler 2, and if you have, for example, eight cores, you can open up to 8 cores, okay, to speed up the compilation process. Okay. So the advantage of multiprocessor, efficient handling of frequent interaction between process, and reduce communication overhead compared to distributed system. Okay. So the application you can have ideal for tasks requiring infrequent synchronization. Remember, because this is quartz, you want to minimize the communication. Remember, the communication is slow on distributed computing and on maybe on the multiprocess. So you want to keep it minimum, okay, in order to achieve more speed up. Remember the MDS laws. When alpha is high, then speed up will be slow. Okay. Okay, then we have medium grain parallelism. The medium grain parallelism is the one that if you are using thread, you have one process, you have one house, and then you partition into rooms so that you can work at the same time. Okay, so this is the process. Process has allocated the resources, allocated the memory, so you just need the path of execution. Okay, or you can say this is the room, and then you can ask one cleaner. Okay, and then you can ask more person to clean the room. Okay, so this is the thread. Okay, you have the process, allocate the resource, and you have here the threads. Okay, so the single application divided into thread, you can see here. Then we have here the explicit parallelism. Programmer define the parallel structure of the application. So you can divide, for example, like this. You have here the SDTV image, SD image, okay, and then you have 4 cores. Okay, you can divide into 4. Like this. One go to core number 1, one go to core number 2, core number 3, core number 4, and then you're expected to have achieved a speed of 4 times. Okay, because now you have divided the processing into 4 threads. Okay. Yeah, so this one will have frequent interaction, so high-level synchronization among threads. Remember that when you have a medium grain, you have more communications. Okay, after finish distributing, then you communicate. Finish distributing, process, communicate, and so on. Okay. So this one requires specialized scheduling, thread scheduling, which is the thread scheduling. And then the decision for one thread can affect the overall application efficiency. We'll discuss more later on when you discuss on multi-thread scheduling. Okay, there are many methods to do the thread scheduling. Okay. So this is suitable for application with tightly coupled tasks needing regular communication between threads. So if you need more communication, then you can use the medium grain parallelism. You can use thread. Okay. Fine grain parallelism, and this is in the instruction level, in the core itself. Okay. Involve highly complex and frequent use parallelism beyond thread-based approach. So this is beyond thread approach. So this is instruction-based. You do pipelining. You can do what you call, you can run multiple instruction at once, or you can do factor processing. So this is the fine grain parallelism. Is even smaller task that you divided. Okay. So this is extremely high level of task interaction and synchronization. Okay, requires fine control. Okay, the challenge, yeah, so this is complex to implement and manage effectively. So there's always a trade-off between the ease of implementation and yeah, the speed up, the benefit that we can take. Okay. So the application typically used in scientific computing because you have the more high level of interaction and you have high level of synchronization. Okay, now let's see if we have, for example, 4 cores, sorry, and then you have here many process. We have the design issue. Okay, depend on the degree of granularity of application and number of process available. So then you have several design issue. If you have 4 cores, it will be different if you have only 2 cores, or it will be different if you have 16 cores. Yeah. So with 4 cores, 2 cores, 16 cores, so you have different. Okay. So the scheduling on multiprocessor involve 3 interrelated issues. Okay, the first one, assignment of process to processor. So the assignment, if you have a process here, process A, process B, then you assign to here, whether you are to stick until finish or not. Okay, or you can move between core number 1 to core number 2. Okay. The next one is use of multi-programming on individual processors, whether it allows here, if you have, for example, C and D, you allow multi-programmings, then A and B, for example, on core number 1 need to interleave. Okay, and C and D can overlap. Okay. And then the second one, the third one is actual dispatching of process. Dispatching, remember when you have the ready queue, and then you can dispatch. If you have one ready queue, you have two cores, and then you need to decide the actual one, dispatch to here, dispatch to here, or if you have two ready queue, and what will happen. Okay, so this is the three design issues that emerge. Okay, when you want to schedule multiple process into a different number of processor. Okay. Now, the design issue, the first one, assignment of process to processor. Remember the different. Process is the program that you run. You have process A and B, C, D, for example. All arrive differently. Okay, and this is the core. Okay, so you want to assign the process to processor. Okay. We can do static assignments. As the name implies, static means it will be fixed. Okay, process are permanently assigned to a processor. If static means A go to 1 and it will stick to 1 until finish. Okay. What does it matter? It matters when you do IO, because remember when you do IO, ready, run, and when you do IO, it will be blocked because IO is slow. Okay, IO is slow, so when you do what you call IO, then to the block. Okay, so the benefit is less overhead, support group or gang scheduling. We'll discuss more later on. And the disadvantage is uneven workload, means the processor one is keep busy, processor two is idle. Okay, that can happen. For example, C and D does not do IO so much, so C and D finish and waiting for A and B, which is IO heavy, to complete the process. Okay. So the other one is dynamic assignment. Dynamic, as the name implies, then you have a global queue. You have only one ready queue, and then it decides which one is free, which one is available. Okay, so better load balancing, but it will be more overhead. Okay, because you need to save the status of the process and then return back when you call again to run. Okay. So the load balancing, you have the dynamic load balancing. The thread or process can move between process queue to balance workload. This can happen if you have one ready queue. Okay, this is ready. Okay, and then you have, for example, 4 process, and you check from these four cores which one is idle. Then you can assign, okay, to the one that idle. Okay. The architecture for process assignment, you can have master slave architecture, means that if you have 4 cores, this is the manager or the master. Okay, the master. Or you can have peer architectures. This is simple centralized control. But if there's some failure or no master, and we can have the performance bottleneck as well. Okay, so there's the trade-off. Okay, peer architectures, all processes are equal and self-scheduled from a shared pool, and no single point of failure, but more complex for the OS design to avoid conflict. So you need to check whether the memory is available, the IO resource are available, and so on. Okay, so this is more complex. Okay, or we can have a hybrid approach in between master slave and pre-architecture. So use a subset of processor for kernel tasks to balance complexity and efficiency, and we can manage difference using the priority scheduling or execution history. Okay. The next issue, the second issue is the use of multi-programming on individual processor, whether we want to allow or not allow. Okay, we can have here static assignment of process. Process are permanently assigned to a spec for processor for their lifetime. What is the necessity of multi-programming? Remember that when you have two programs, for example, A and B, okay, A is doing IO, and you need to remember that this part is very long. Okay, this part is very long, maybe 1,000 times. You need to put, this is the processing part, and this is the I/O part. It's very long. Okay, so that's why we want to have multi-program. In the moment the A is doing I/O, they can switch to B. B can use the processor. Okay, maybe there's a C also. C can use the process, and then it can go back to A to finish. Okay, so you can see the multi-programming is used to have the high utilization of processor. Okay, particularly when process is blocked or doing I/O like this. Okay, remember this one also has around 1,000 times slower compared to this, the processing part. Okay. And we have a coarse grain synchronization. Multiprogramming is essential to maximize processor utilization. Okay, the coarse grain, remember you have multi-process. Okay, you have multi-program. Okay, or for medium grain applications, we can this one will be less critical. Okay, where the focus is to save the overall application performance. Okay, this is the thread. Okay, using the thread. Okay, and yeah. So this is the issues on the use of multi-program on individual process. The third issue is the actual process dispatching. What's the dispatching? Remember, you have the ready queue and you have run. If you multi-core, then you can have here the one and two. Okay. So the scheduling, this one, unit process scheduling. Remember, that you can have first come, first serve, round robin, shortest process next, shortest remaining time, highest response ratio next. 1, 2, 3, 4, 5. Yeah. So at least you have this algorithm. Okay. So on multiprocessor later on we can prove that the simple scaling algorithm, for example, first come first serve, is effective because it has less overhead. Remember that first come first serve, we just run the one that comes first. Okay, and because the complex algorithm can introduce unnecessary overhead, you need to calculate more. Okay, you need to decide more. Okay. So this is if then we have an thread scheduling challenge. With thread, the new connection arise at the synchronization dependency and resource sharing. Okay. So remember that when you have threads, okay, the one process, and then you have thread one, thread two, and remember that the thread can access the same memory. Okay, thread one, thread two can access the same memory. So there's the issue on synchronization. There's issue on especially when you write the data. Okay, for example, thread one update the status to -1. There's some error. Thread two update the status to 0, which is okay. So then there's confusion whether it is okay or not okay. Okay, so you have need to do the synchronization there. Okay. So, okay, for the process dispatching, we focus more on efficiency rather than complexity. Okay, so the multi-process system benefit from reducing scheduling overhead to improve scalability and throughput. Okay, so remember that uniprocess scheduling, you have at least 5 algorithms. Okay, for multiprocessor, maybe simple first come first serve is sufficient. Okay. Okay, then we also focus on multi-threadings. Yeah, so this managing dependency between threads, whether it yeah, so we access the same resources, for example, it become critical for to achieve optimal performance. Because remember, another things that become the alpha is the critical section. If you have more critical sections, mean you have bigger alpha, means slower speed up. Okay, this is, for example, the critical section. Want to update the status, that will be critical section. Means that you need to have the mutual exclusion. When you have mutual exclusion, then you need to see one by one. You can see there's some bottleneck here. This is the critical section. Okay, so you need to optimize this, minimize as much as possible. Okay, so that you can achieve a optimal performance. Okay. Okay, now let's move on to the process scheduling. Okay, so we can have the system normally use the single queue for all processor or multiple queue based on priority, feeding the processor pools. Okay, the system can be modeled as multi-server queuing architecture. So the scheduling, you can use first come first serve, round robin, shortest remaining time. Okay, and normally we measure the variable in service time. Remember when you do the process, we have process when it is arrived, arrival time, and the service time, how long it will run. Okay, so process A arrive at 0, service time is 3, arrive at 2, service time is 6, for example. Okay. So the variability in service time, so 3, 6, 4, 5, 2, this is the variability. We can measure using the variation coefficients, which is the sigma divided by mu. Okay, the sigma is standard deviation and mu is the mean service time. So you can take average, you can calculate the sigma, and you can have a CS. Okay. So low CS mean low variation. So this is equal surface time. So for example, there's not too different, maybe between 3, 4, 3, 4, 3. For example, this is not much. But if you have high CS, then you need smarter scheduling. For example, one is 3, one is 10, one is 100, for example, then you have here more variability. Okay. So the real world scenarios often see CS larger than equal to 5. So indicating significant variabilities. Okay. Yeah, so you can see here, throughput comparison, if you are using single processor, this is the coefficient of variations. Okay, so when it is not vary, it's almost the same. Okay, but when it is vary, like in one running Microsoft Word for 3 seconds, one running PowerPoint for 100 seconds, for example. Okay, for example, you have here 5. You can see dual processors, the throughput ratio is almost similar. What does it mean? It means that remember that round robin is more expensive because you need to check 3 times. Okay, when the process arrive, when the time quantum expires, and when the process finish. Okay, 3 times that you need to check. While the first come first serve only when the process arrive. Okay, so you can see dual processor is almost similar. Only have 101 or 1.04. Okay, the difference between round robin first come first serve. Okay. So this is all using dual processor. Now, if you have 4, it will be smaller. And you can see here also shortest running time to first come first serve. Okay, this is single processor. Uh, Means that the performance is much better compared to round robin. You can see 1.2. This is only 1.15. Okay, but when you are using dual processor, it's almost similar. Okay, 1 or 1.05. Okay, means that the the simple algorithm can achieve the performance of complex algorithm. Okay, so that's why we can see here, simple strategies may be sufficient for multiprocessor system. Okay. Okay, so yeah, so you can see the findings, the what you call the experiment here. The finding constantly support that reduce sensitivity to scheduling discipline or scheduling algorithm. You can choose any algorithm, but if you can choose any algorithm, means that you can use the simple one. Okay, which is the first come first serve. Okay. Okay. Now let's move on to thread scheduling. Remember the threads is one process. Then you have the part of execution. Okay, you can have more part of execution. Okay. So the thread enable so for example, in here, like when I'm doing now, one record the video, one thread record the video, one thread record my my input, and another thread display the PowerPoint. Okay, so you have at least 3 thread, and 4 thread record this PowerPoint presentation. Okay. Okay, so we have yeah, we can do concurrent executions. The thread provide program structuring aids and overlapping I/O with processings, and low overhead in thread switching compared to the process switching. Okay, so if you're creating more process, you have what you call more overhead. Okay. Okay, so this is the uniprocessor benefit. Okay, and then let's see the benefit for multiprocessor advantage. So this is if you have only one processor. Okay, and this is if you have multiple core, for example, 4 cores and so on. Okay, so this is really there now. So we have the popular one or the normal one, the usual one is the multi-cores. Okay. So the thread exploit true parallelism means that you can, as you mentioned earlier, start from the process. Now you have part of execution. So this is the true parallelism. You have focus and you have part of execution. Initially, you only process by this image, for example, processed by one core. Now you can divide the work and process by 4 cores. Okay, so this can result in significant performance gain, depends on the number of cores, and also the depend number of the alpha. Okay, the serial portion of the parallel program. Okay. So for task scheduling, the interactions it requires that significant interaction, because this is what we have here. Okay, for the medium grain, we already divided the work, so there are significant interaction between thread 1, thread 2, thread 3, thread 4 if you have 4 threads. Okay. Okay, so let's move on. So for thread scoring, there are uh, 4 methods. The first one is load sharing. The second one is we can do gang scheduling. Okay, the third one, dedicated processor assignment. Okay, so one thread, one process. So let's say you have here one process, and then you create 4 thread, for example, thread 1, thread 2, thread 3, thread 4. And then you have core number 1, core number 2, core number 3, core number 4. So you can pair thread 1 to core number 1 until thread 4, core number 4. So this is the dedicated process assignment. It will not change until the program completion. Okay. Or you can do also dynamic scheduling. Let's see the pros and cons for each method. Okay. So for load sharing, the idle processor dynamically select thread from a global queue. So what does it mean by global queue? Remember that we have the state ready, and then we have the state run. If you have 4 core, means you can run uh, uh, the run state can be 4 times. Okay, so this is global queue. It select the queue, okay, and then it select which one is idle. If this is idle, then put it here. If this is idle, this is occupied, okay, then you don't select. If it's idle, then you select this one. You can distribute the work to the idle processor. Okay. So the gang scheduling, related thread execute simultaneously. Related threads mean here normally the threads belong to the same process. Okay, so the threads belong to the same process. Okay, related threads execute simultaneously. Then you can see here thread assign fixed processor. Remember that this one also you can have this process 1, you can have also process 2. Process 2 you have also 2 thread, for example, thread 1, thread 2. So this depend processor 1 or process to C2. Okay, so you can also do like that. Okay, you can allocate the threads according to the cores. Okay, the last one is dynamic adjustment of the thread count during execution for workload adaptability. So this one will include more complex algorithm, okay, to schedule the threads. Okay. So let's see the first one. The first one, load sharing. Remember load sharing. So you have one queue, and then you have 4 core, for example. So even distribution, you can ensure that one go here, the next go here, the next go here, then the next one go here, and the fifth one will wait until which one is idle. Okay, which one is available. Okay. And also you have here the centralized schedulings, flexible queue managements. Okay. So this is the advantage. The disadvantage can be we can have queue bottlenecks. For example, it can run for other things, but you have the bottleneck in the queue here. Okay. And we have also the disadvantage cache inefficiencies. So preempted threads, the one that is stopped or blocked, may not resume on the same processor. Okay, reducing the cache effectiveness. Why is that? You can see. So for example, this is core number 1, this is core number 2. It has level 1 cache, it has level 1 cache also. So if the thread 1 initially go to core number 1, okay, and then it move to core number 2, then it cannot use the cache on the core number 1. Okay, it need to copy first on the core number 2 cache, L1 cache. Okay. But despite then also the thread coordination, okay, the thread of program may not execute simultaneously, impacting performance, requiring high synchronization. Okay, high synchronization means bigger alpha. Bigger alpha mean lower speed up. Okay, because the alpha several portion of the MDOS loss, including synchronization, I/O operations, critical section, and communication. So any communication, any critical section, any synchronization, it will contribute to the higher alpha. Okay. But again, despite this advantage, load sharing is widely used in modern because of it's simple. You just need to have one queue here. Okay. So one queue. Okay, so then load sharing, we can, the scheduling policy can use first come first serve, smallest number of thread first. Okay, this is for example, process number one has 4 threads, process number two has 2 threads, so you allocate this one first. Okay, or you can also, the next one, preemptive smallest number of thread first. So job with fewer thread, preempt currently executing thread. So if P1 run first, because P2 has smaller number of thread, then it can preempt means stop P2, stop P1 and then run P2 first. Okay. Okay, so let's move on. This is another example, Mac OS examples. You have also can have a local, this refined load sharing. You can also have some variation. For example, in Mac OS, you have local and global queues. Okay, and yeah, so the bound thread used for dedicated. So this in between the load sharing and dedicated processor. Okay. Okay, so gang scheduling, the simultaneous scheduling of all thread within a single process across multiple process. Okay, so this is ideal for medium grain to fine grain application. The advantage is reduce synchronization blocking, minimize process switching. Remember, the process switching is expensive. Okay, so if you want to switch, for example, you have process one and you have 4 threads. Okay, you have process two, you have 2 thread, okay, thread one, thread two, thread three, thread four, okay, thread one, thread two. So thread switching is less expensive than process switching. Okay, because process switching includes several more steps. Thread switching, your resources are already there. Um, process switching is like you are moving from one house to another house. You might have the key, you might need to knock the door first. But if you belong to the same house, you can move to different room easily. Okay, so that's why the thread switching is less expensive compared to the process switching, like in our case, like home switching. Okay, you can also optimize resource allocations and without additional locking overhead and lower scheduling overhead. Okay, the performance benefit, we have what you call increased efficiency for parallel application. So let's see the example. See the example. Okay. So we can see here the challenge is uniform time slicing equal allocation, which might not be easy to implement. Okay, so you can implement a gang scheduling. So the first one is uniform scheduling. So it doesn't matter whether you have how many threads. Let's see here, this processor. Okay, and this is process one, process two. Let's see, this is processor. Let's rename this to core number one, core number two, core number three, core number four, and this is process number one, number two, one, two. So for example, you are on the round robin fashion. You continue until process is finished. Okay, so one, two, P1, P2, P1, P2, P1, P2, and so on. Okay, if you do like this. Okay, then you have wastage here. You can see you have 4 cores, but 3 cores during the execution of process number two, it will be idle. Then you can find 1, 2, 3, 4, 5, 6 in this up to 4 seconds. 6 over 20, you have 30% waste, okay, or idle, okay. In which if you have you have weighted scheduling, means that the more threads, then you allocate more. So this is like a gang scheduling. Okay, so you allocate here P1, P1 again, P1 again, P1 again, because P1 has 4 threads, and then P2 because P2 only have 1 thread. Then you can see the idle only 3. So 3 over 20, 50%. So you reduce the wastage from 30 to 15%. Okay. Okay, then the third one is dedicated processor assignment. Dedicated mean now you have the thread, not only the process thread. Okay, then you have the core, the processor core. Then thread one go core number one, thread two core number two until it finish. Okay, what is the benefit? There's no process switching. Okay, because you are on the thread. Okay, on the thread level. Okay, and simplify scheduling. No need for dynamic processor reallocation. For example, if you don't do dedicated, then T1 uh, go to C1, T1 can go to C2 as well. Okay. So, and this is suitable for highly parallel system in which we have tens or hundred of processor. means that hopefully like NVIDIA, for example, NVIDIA has GPU has 1024 cores. Let's say the thread is 800, and you can easily make the dedicated processor for threads. Okay, because you have left with the idle to do something else. Okay. The challenge is underutilization of processor. For example, C1 occupied by T1, okay, for a long time, okay, and C2 already finished, okay. So this is idle process, inefficient resource because this is the thread from process number one. So thread number two cannot use this core, okay. Okay, so dedicated process assignment. Let's see the example here. Let's see. We have this is the result. Speed up. This is number of thread per application. We have two application, which is matrix multiplication and FFT. That is computationally intensive. It's not I/O intensive, but it is computationally intensive on a 16 processor. Okay, so each application varied number of threads. So you can see one speed up is one, two, 1.8, 1.8, and continue. And you can see here, I can highlight this. This is the highest. You can see this is the highest. Okay, so what's the take? The take is you need to the active thread limit the active thread to the number of processors. So if you have this is 16 processor that able to create 16 hardware threads, okay, that run 16 thread at the same time. So this is 8 plus 8 altogether is 16. So you match this 16 thread, 16 active thread for 16 processor. Okay, 16 active thread for 16 processor. What if you have 4 application? Then it may be 4 because 4 times 4 is 16 and so on. Okay. Okay, so the optimal is when you add here, matching the total number of processors to 16. We have seen this one. So if we have more, then if we have more thread than the available processor, remember that this is a software thread, okay? And the actual one, you need to match with the hardware thread. The one in the processor is hardware threads, okay. And this is a software thread. You can create so many threads, but the one that is actual running is limited by the number of cores, okay. Okay, so because of excessive preemption, critical section delays, and efficient cache usage. Okay, so this is the summary that you need to limit the total number of active thread to the number of processors. Okay. Okay, the difference between gang scheduling and dedicated processor assignments. This is like memory allocation. Processor allocation in multiprocessor resemble memory allocation in uniprocessor. So you have one. This is memory. Okay, so divided into pages. Okay, divided into page. So the challenge is determining how many processor to assign to a program. So like how many page frame assigned to program. This is, for example, this is 3-page frame. This is process A. This is process B. Okay. So they represent the minimum number of threads. So in order to run smoothly, how many pages need to run here? The same thing like when you in the process allocation, how many threads should run? Not all. For example, precisely what we have process one with 4 threads. We have process 2 with uh, 1 thread only. Okay, in our gang scheduling example. Okay, maybe out of these 4, we don't need all. Okay, the one that can keep active maybe 2 threads. For example, in the case of PowerPoint, you don't need to activate every time the automatic saving that will run every 10 minutes. Okay, so you don't need to run the threads. Okay, every time. Okay. Okay, so and yeah, so this is what you call similar like memory allocations. So you need to set the minimum number of threads, and failure to schedule the full actively working set leads to processor crashing. Means that you need actually 3 threads to run, but you only load 2. Okay, so you only run 2. So there's processor crashing. It keep repeating. Should I run? Can I run? You cannot, and load again, and so on. Okay. So it will be schedule, this schedule, schedule, this schedule. Okay. So we have also processor fragmentation in which level of processors are insufficient in number. Okay, not enough. Okay, for example, this one occupied by C. So this is fragmentation. You don't have D, for example, require 4 threads. So you cannot run this one. Okay. So this one lead to inefficient resource allocation. Okay, so the solution you can use gang scheduling, or you can use dedicated processor assignment. Okay, the last one for thread scheduling is dynamic scheduling. So dynamic scheduling allows runtime adjustment. So it depends from time to time. Okay, that's why the term is dynamic. Depends on the state of current time. It might be different from the next time. Okay, so this one enable better utilization by adapting to changing system and application requirements. Okay, but this one need to have a collaborative approach between the operating system and the applications. Okay. So the OS will partition processors among jobs, then application will decide which thread to execute or suspend within their partitions. Okay, so you have 4 cores, for example. Okay, this one decided by OS. You process A can use 2 cores, but which thread that one need to be decided by the process. The process. Okay, the OS will only decide you can get 2 cores. Okay, and then the the application will decide which thread that is important to run. Is it T1 and T3? Is it T2 and T1 and so on? Okay. So the process allocation policy, when process request, you assign other process to fulfill the request. For new job, they allocate processor from existing job with more than one processors, and you need to check again if it is available or not. If not, then the request is idle. Okay, you need to wait. Okay. So then also we have when processors are released, assign processor to waiting job with no processors for new arrival, and otherwise we can use first come first serve. Okay, so we have better utilization and superior performance compared to gang scheduling. But the drawback is we might have a potential overhead. You need to check whenever you have the complex or dynamic. There's not statics. Then there's a potential overhead. Okay, so we need to test with the real world application. Maybe some is better using gang scheduling, okay, or maybe it's better to use dynamic scheduling. Okay. Okay. Then we have another issue. This is the last section. Multi-core thread scheduling. So we have traditional scheduling limitation, and we need to focus on minimizing off-chip memory access. Okay. Let's see what it mean, because we have sometime L1. We need to really utilize the concept of cache memory. Okay. So if it is on L1 cache, then we need to better fully utilize the L1 cache, whatever the size is, L2, L3, and so on. Okay. And there is further complicated by the structure or the architecture of the difference between Intel and AMD. Okay. So the OS normally use load balancing to evenly distribute threads among cores. So this one prioritize process utilization, but might not leverage the full performance benefit. Okay, so maybe for example here you have core 1, core 2. Maybe it's better to see it here. So like this one. We have here core 0, core 1, and we have level 1 cache. And in AMD, we have level 2 cache share. You can see this one. Okay. Then after that, core 2, core 3, core 4, core 5. You have level 2 cache share, level 2 cache share also. So it's whatever data in here can be read either by this one and this one. So the normal windows will allocate anything that available. But if you are working together, the thread is within the same process working together, it's better to allocate closer. Okay, for example, P1, thread 1, thread 2, thread 1, thread 2. So it can working together here on core number 0 and core number 1, specifically on the adjacent cores. Okay, so that they can use the L2 cache optimally. Okay, they can use better the L2 cache. Okay, so that's what this mean here. Okay, reducing of chip memory because we have also the shared cache architecture. Okay, like I mentioned here. Okay. Okay. Okay, then yeah, so this one I already explained. The AMD bulldozer, for example, share L2. Okay, the adjacent core share cache. Okay, they can benefit if you share if you what you call run thread one on core number 0, run thread 2 on core number 1, because they are sharing, they can share the data on L2 cache. Okay, which is faster. So this is on chip. Okay, if you go to memory, this is off chip because you have CPU, and then you have DRAM, okay, dynamic random access memory here. So this is off chip. You need to go to the memory here. If it's everything on the on chip, okay, on the cache, even in here, okay, then it is better. Okay. Okay, so to cache sharing aspect, you can use cooperative resource sharing. So thread sharing memory resource benefit from being adjacent cores to enhance locality, like we see here earlier. Okay, and resource contention, thread competing for shared cache degrade each other performance. So this is contention aware scheduling. Okay, which try to minimize this conflict. So we want to optimize shared cache utilization and minimize off-chip memory access. So this is contention-aware scheduling. This is another type of scheduling that tailored to the multiple level of cache and then the architecture of the processor. Okay. Yeah, so the emerging challenge will be the thread to core allocation, how to allocate the thread into the core. Okay, so that will be the first section part of this chapter. Okay, and now let's see the example. Okay. Previously, what we have here was the takeaway. Uh, what you call the simple algorithm is sufficient for multi-core. Okay, simple algorithm. What does it mean is first come first serve. That there's very low overhead. You just see when they are coming, arrival time, and then they just serve based on the arrival time. So A, B, C, D, E. Okay, it's not like surface shortest process next. You need to see the shortest. Okay, then it will run next one. Okay. Okay, so now let's see here. So when you add this is 20. So you can prepare 20. Okay. This is from the previous chapter. So you have A, B, C, D, E. Okay, so 10, 5, 15, 20. It's not that. Okay, hold on. Let me erase this. Okay. Okay, just repeat later on your own. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, 20. Okay, so first come first serve is easy. So 0, 3, run, and you need to mark this. Okay, this is arrive. Okay, and then you arrive, another arrive is 2, means it's not there, it's not in the queue, but this 2 is already in the queue. Okay, then you have 4. Okay, and D is in 6. Okay, and E is in 8. Okay, so you can run this. After it's finished, then you just wait for 1 second, then you continue. 6, 3 plus 6 is 9, so it run until here. Okay, the second process is run until here. Okay, 3, 6, and then 4, you run from here, from 9 until 13. Okay, so you go here. Okay, 4. Okay, D, you can see this the waiting time here. Okay, D, even long waiting there, 5. Okay, so from 13 to 18. Okay, so this is 5. And the last one is the longest one is 2. So altogether requires 20 seconds. Okay, now let's see if you have dual core. What you see here previously is single core. Now let's see if you have dual core. Okay, A, B, C, D, E. Okay, the same thing. Maybe we prepare it. It will be faster than the single core. 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, maybe 15 only. Okay, now let's see here. Let's mark the arrival time first. This is 0. B is in 2. This is 4 and 6 and 8. Okay, so now let's how to have different color. Okay, just I'm using the black. Core number 1. Core number 1 run first come first serve. Okay, you go to here. 3. Okay, this is core number 1. Okay, remember that we have dual core. Core number 1 and core number 2. Okay, so we have core number 2 and we have core number 1. Okay. Okay, then you can see here, it's arrived here. No need to wait core number 1 because you can run core number 2 is available. So you can run 6. Okay, so you can run from here, the arrival until 6. 2 plus 6 is 8. So you can run here. Okay, can run here. This is core number 2. Can run for 6 seconds. Okay, then core number 1 is idle. This one unused. Unused. Why is unused? Because there is no more process in this particular time. From 3 to 4, there's no more process. At 4, then there is process C. Then you can allocate there. Okay, allocate 4. 4 plus 5. 4 plus 4, 8 also. So you can see. This one is core number 1. Okay, now you can see this is board idle. Okay, in this location board idle, but D is waiting. So the only waiting is only D here. Okay, so D is waiting for only 2 seconds. Okay, waiting for 2 seconds. Then you can allocate. This is either one. It can be, let's say this is core number 2. You can allocate that. So it will be 5. 8 plus 5, 13. Okay, this on core number 2. And this is on core number 1. Core number 1, which is 2. So you can see altogether only requires 30 seconds. Okay, speed up 20 over 13. Okay, if you have 10, then it will be twice. You have 2 cores, you expect twice. Okay, but this one is 13. So the speed up is around 1.5. It's good enough. Okay, 1.54 is good enough. Okay. You try later on using the this is the optimum algorithm for uniprocessor. Normally you have shortest remaining next. Compare uniprocessor with the dual core. It will produce the same result. Okay, so you just try later on. Okay, so I think that will be for this part, first part of this chapter, and I'll continue later on for the next part. Okay, thank you.